Hi everyone. For this Choose Your Own Adventure lab, I have selected a lab on pendulums. We will focus on the time periods of pendulum motion. A pendulum has a mass called a bob, which is supported by a rod or a string, and it moves in a circular arc motion, and in this case we will neglect air resistance in the bob's motion because it is negligible. The force of tension does not do work on the bob since tension acts perpendicular to the bob's movement. So therefore, the focus of force on the bob will be only on gravity. In this lab, we will look at the motion of a grandfather clock's pendulum. I uploaded a video of a pendulum to Tracker of a grandfather clock. And I placed a piece of tape on the bob to help me choose accurate and precise points of mass in Tracker. As you can see, the calibration stick is set to 0.21 meters, which is the diameter of the bob, and the coordinate system is just centered in the middle of the bob with the positive x-axis in the right direction. So as we play the footage from Tracker, you can see that I mark the point center of mass on the tape with the X on it in the middle of the bob, and we have a nice graph created by it. So looking at the graph created in Tracker, we look at our experimental time period, which is when the pendulum basically makes a complete swing. So we're going to be looking from one apex to the next apex. So the time changes from 1.07 seconds to 3 seconds when x is both 0.12. So that's when the bob makes a complete swing, and that time period is 1.93 seconds in the experimental data. So now we'll compare this to a computational model in VPython. I modified code found online on the University of Toronto's physics website, and this code plots a swinging pendulum, and I inserted the equation of a pendulum's time period, which is t equals 2 pi times the square root of L divided by G. And L represents the length of the rod supporting the bob, and G is the gravity. When we run the code, we'll see how that works, but I have inserted the equation into the Python file, and I also accounted for gravity, 9.8 meters over seconds squared, and also the length of the rod supporting the bob, which was 0.92 meters. So here we have our code, and we'll run it and see how it looks in comparison to our experimental data. Okay, so here we see the computational model of a pendulum swinging, and we are able to see the estimated time period, which is 1.925 seconds, which is fairly close to our experimental time period, which was just 1.93 seconds. So the reasons for the minute differences would include human error in plotting points on Tracker and in collecting measurements. But overall, the computational model using the equation for a pendulum's time period was pretty accurate, regardless of any error that happened in collecting any data. So overall, the pendulum's time period was pretty accurate and consistent with the computational model and the experimental model.